So let's begin. So today we have the pleasure to listen Lei Zhao from Augsburg University about the maps to Z-square.
Yeah, thank you, Alan, and also I thank the organizers for the invitation to speak here, and also happy birthday, Hildeberto. I had the pleasure to meet once in Spain and another time in Paris. Okay, so I would like to try to explain what I think, what I thought with this mapping, and in particular its applications in some problems in selection mechanics and related stuff. So I hope this is a simple talk. So okay, let's start. Oh. So this is right. So the mapping which I would like to talk about today, very simple. So it's complex square mapping, same Z to Z square. And this mapping does quite some wonders in classical and selection mechanics, and which are mostly well known. So first, this mapping induces a correspondence between the planar Hooke and Kepler problems, somehow showing that the Hooke problem of a pair of harmonic oscillators and the planar Kepler problem are in a sense equivalent outside singularities. And because the collisional singularity in the Kepler problem with attractive center is singular in the Kepler problem, but then it got transformed into a non-singular center in the Hooke problem. Therefore, it regularizes this singularity in the Kepler problem. And what is more is that this also extends to regularly perturbed Kepler problems. Therefore, many applications in selection mechanics. So, and also, we see that the Kepler problem is not separable in natural Cartesian coordinates, while the Hooke problem is separable. Therefore, another very simple observation is that this mapping separates the Kepler problem, and again, this property to separate problem also extends to some other problems, so which we will also briefly discuss. And before to discuss more about this complex square mapping, I would maybe first mention some variants of this mapping, which also appears in the literature and in the study of this whole subject. So, of course, a natural generalization for the mapping Z to Z2 would be the mapping Z to ZK, and we see that such kind of mapping regularizes homogeneous potentials with these exponents, so 2 over k minus 2, as has been shown by McGehee. And indeed, McGehee shows that only these exponents are block regularizable, and precisely this mapping regularizes this type of potentials. And then this is another variant which was used by Birkhoff to simultaneously regularize the 2 double collisions of a perturbed 2-center problem, for example, the restricted 3-body problem. And here we see that the mapping is so this mapping fixes 2 points, 1 and minus 1, and while Z to Z square fixes the point 0. But if we consider this both of these mappings as on the Riemann sphere, so C union infinity, then Z to Z2 fixes 0 and infinity, and 2 to 1 otherwise, and this mapping fixes 1 and minus 1 and 2 to 1 otherwise. So Z and Z minus 1 will be sent to the same image. And indeed, what Vogel also showed, so that indeed these 2 mappings are conjugate by a Möbius transformation on the Riemann sphere. Therefore, it's really a variant of Z to Z2. But this is very useful because it simultaneously regularize so double collisions with 2 centers. And then this is a mapping for which one read Q as a quaternion. So then this mapping will send a quaternion to a quaternion with 0 real part. So so the conjugate of a quaternion times I times the quaternion, if we conjugate it, then we see that it's going to be the negative of this quantity itself. Therefore, its real part is 0. Therefore, this is a mapping from R, well, let's say, for the underlying real space from R4 to R3. And this is a mapping which Kusa-Hamel-Stiefel showed that it can be used to regularize the spatial Kepler problem by essentially 4 harmonic oscillators, so 4 isotropic harmonic oscillators. So these are a small list of variants of this complex square mapping. Okay, so we'll first start by recalling this rather simple procedure of the Hooke-Kepler correspondence. So we just go through this Hamiltonian formalism. So this is a Kepler Hamiltonian with with a mass factor S, which we fix its energy at minus F, which is the same to say that this quantity, so Hamiltonian, so kinetic part plus potential plus F equals to 0, and this defines certain kind of hypersurface in the phase space. And now what we can do is that we can now multiply both sides by the quantity norm of Q, and indeed, as long as norm of Q does not equal to 0, then indeed this describes the same hypersurface as the previous one, and therefore they have the same characteristic foliation, and so which means that the corresponding vector field, the corresponding Hamiltonian vector field, restricts to these energy levels are the same up to a time reparameterization. And indeed, here one could show that the time reparameterization is exactly given by this factor norm of Q, as can also be otherwise simply verified by writing down the Hamiltonian equations. So and now we just pull back this Hamiltonian by this by the cotangent lift of the complex square mapping. So we have the complex square mapping on the base in the configuration space, and now we complement it into a canonical mapping. So it will then keep the canonical symplectic form invariant. And then it will also pull back the Hamiltonian, as we have shown above, into this Hamiltonian here, which is just this norm of W squared over 8 plus F times norm of that square minus S equals to 0. And this is just the Hooke Hamiltonian with well, some kind of a string constant F and with energy S. So it's a very simple procedure, which also we see that there's no singularities for the set Z equals to 0 in this Hooke Hamiltonian, corresponding to the singular set Q equals to 0 in the Kepler Hamiltonian. Therefore, this somehow brings a regularization. And what's also kind of interesting to see is that here the role of S and F somehow exchanges. So before S is a parameter of the system, and F is so minus F is energy, and in this case we see that so S essentially gives you the corresponding energy, and F is now a parameter of the system. So now we just extend this procedure very simply to some perturbed Kepler problems. So we, for example, we made just for the purpose of simplicity, let's assume that we perturb the Hamiltonian by some regular function v of q, so of a regular function of the configuration. So we just perturb the potential, and the same procedure applies. We now still do this time reparameterization, and we pull back by the cotangent lift of the complex square mapping. So what we see here is that if we start from a regular function v of q, then in the end, what we get is a regular system, and the perturbation now becomes norm of z square times v of norm v of z square, and it's kind of nice. So what one could see is that we have this norm of z square factor, which is regular but which becomes small when that is small. So previously we are perturbing a singular problem of the Kepler problem by some regular perturbation. So what one could think is that the perturbation will be dominated in the neighborhood of the singularity. So as long as you are very close to the singularity. And after this transformation, we see that the singularity now disappears with some kind of reasonable strength, but now the perturbation becomes small when we approach this center. So this transforms the system in such a way, which is very nice. So and then what one might see is that still this type of regularization also extends to some forced Kepler problem, meaning that we may also allow that the potential which perturbs the Kepler potential to be dependent also on the time t. And for this, we do the same procedure, but on the extended phase space. So we embed this time-dependent system into the zero-energy hypersurface of this extended Hamiltonian on the extended phase space. So which means that here tau is a conjugate variable to t, which we now should consider as a position, well, as a space variable. And in the end, the parameterization with respect to this t will give us the right time parameterization of an orbit. But in this extended phase space, this is our Hamiltonian, and the time is now fictitious, so it doesn't have a real physical meaning. But it's kind of nice to have this formalism, because then we can just do the same thing. So we multiply both sides by norm of q, and then we pull back by somehow the natural completion of the mapping z to z square. And here there's an issue about the variable t, which is now the space variable, that one has to shift it somehow in order to keep this whole mapping canonical. But then again, what we see is that again the center of this perturbed Kepler problem is again regularized with a perturbation term, which is also now becomes small as long as z is sufficiently small and if v is regular and bounded. So it is essentially this procedure which has been used to study the problem of finding the so-called generalized solutions of a periodically forced Kepler problem. So we see that in the Kepler problem we have this collision ejection orbits which somehow naturally brings a regularization to collisional orbits. For many reasons, we might tend to also accept these collision ejection orbits also as periodic orbits in a generalized sense. And precisely this type of generalization can be also formulated for a periodically forced Kepler problem, and then the problem is to count how many of this type of orbits we could get. And this is a subject which has been studied by myself, but also with many other colleagues and collaborators. Here's a name from Italy and from Spain. And so some results I would like to mention. So with A.Boscaggin and R.Ortega, we apply really just this regularization procedure in extended phase space technique to this periodically forced Kepler problem, and there we show that there are many generalized periodic orbits as long as this forcing term, so this perturbation term, is assumed to be sufficiently small. So for any prescribed number, we may determine a large size of the perturbation, and for such perturbations, we will get at least this many number of periodic orbits, which might be understood in a generalized sense in the sense that it might get past the collisions. And then, so in this paper, we assume that this forcing term is everywhere regular, but it's actually not really needed. And therefore, I made some kind of completion with Raphael Ortega to just to remark this. So it does not have to be regular everywhere, and it's enough for it to be regular in the neighborhood of the attractive center of this Kepler problem. Therefore, admitting also applications to the restricted three-body problem, which has another center which moves around and so on. And then in another paper, Vivina Barotero, Gianmaria Vaccini, and Raphael Ortega applied a regularization technique in a variational setting and showed that there exists infinitely many generalized periodic orbits when the fourth term is globally regularly well defined. This is of a rather new and very different method. So here one sees that the number increases to infinity. And then I got rather inspired by their very nice result. And then I was asking whether there is something which one can do to try to understand it again with this regularization in extended phase-based techniques. And then in the end, what I get is that if one applies these techniques, and then with the help of some other techniques from syntactic topology, then the result is that there are infinitely many generalized periodic orbits already accumulates at the attractive center of the Kepler problem. So already in an arbitrary small neighborhood of the attractive center of the Kepler problem, one finds there infinitely many generalized periodic orbits, and this is a result which applies to the, for example, to the restricted three-body problem as well. And so this result I obtained also in all dimensions, but in dimension 2, really the result can be obtained via this complex square mapping techniques to regularize the singularities in extended phase space. But I mean, there are many applications of this kind of regularization techniques. There's a rather limited list, but just to indicate somehow our thought on this type of application. And then we may just do the same type of thing and try to look at a slightly different question about the separability of some perturbed Kepler problems. So really we do the same thing. We take this perturbed Kepler Hamiltonian, so where the perturbation is so V of Q, and then we pull back, we get into this Hamiltonian as we have already seen. And now the remark is very simple. We see that the first part, so when V is 0, then the system is just a pair of isotropic harmonic oscillators which separates in that W variable. Therefore, this system will be separable as long as this perturbation term is the sum of two functions depending solely on Z1 and Z2 respectively. It's very simple. You add it and then the system is separated. Therefore, as a result, or well, just very simple remark. So here one may essentially choose V1 and V2 kind of arbitrarily. And therefore, there are infinitely many systems which are separable via this complex square mapping. And this is somehow like the simplest non-trivial example, which is just the so-called Stark problem, that we add just this linear force in one direction to the Kepler problem, and precisely this procedure brings a separation to the Stark problem, for which even its integrability is not so easy to see if we don't employ this procedure. So it's very simple, but somehow it applies wonderfully. We shall come back to this point of separability a bit later. And I would like to talk about something which is called which we call mechanical billiards. It's a different topic and should maybe not be considered as part of selection mechanics. let's say as more general dynamical system question. So by a mechanical billiard, we refer to a model that a particle moves in a force field and get reflected elastically against some reflection wall in the configuration space. So here somehow the complexity increases a bit by the existence of this reflection wall. So, for example, when the force field is 0, then of course this kind of stuff just reduces to the usual Birkhoff-free billiard, which is a subject object of a lot of studies. So it just particles moving along straight lines and get reflected against some reflection wall, for example, in the plane and against some curve, and then of course its dynamics is determined strongly by this reflection wall. And for all these mechanical billiards, one of the variety observation is that because of the elastic reflection law, so the angle of incidence equals to the angle of reflection, and therefore the kinetic energy does not change at a reflection because the velocity does not change. It's not so the norm of the velocity does not change, while only the direction of the velocity changes before and after reflection. And the potential would be just what it is at this point of reflection at this reflection wall. Therefore, the energy does not change before and after such a reflection. And now let's restrict our situation to planar problems for simplicity. And therefore, in a planar problem, a mechanical billiard is called integrable if an additional first integral independent from the total energy exists and can be identified. So as one might expect, then in the end, if one considers the corresponding billiard mapping, then we will have integrable discrete mapping, and the dynamics of such an integrable mechanical billiard are in principle regular, while in principle a non-integrable mechanical billiard may exhibit rather quite some chaotic behaviors and so on. Okay, so now we will come back to this question about finding integrable billiards, integrable mechanical billiards with the underlying force field being the Hooke one or the Kepler one. So it's kind of tempting to try to look at this kind of problem and try to relate them, because again, a very simple observation is that the mapping Z to Z2 is conformal. So it preserves the angles. Therefore, if the angle of incidence equals to the angle of reflection in one of the systems, and it will remain to be so in this corresponding system, which means that the law of reflection corresponds to each other under such a conformal transformation, and therefore the billiard trajectories will also correspond to each other. Therefore, really, this Hooke-Kepler correspondence by the complex square mapping can be extended to Hooke and Kepler billiards, so not necessarily integrable. But on the other hand, there are various reasons that somehow one finds a bit more integrable Hooke billiards. The result is that essentially those with a conic section reflection wall centered at the Hooke center are integrable. So the corresponding billiard systems are integrable, and somehow it's kind of late that one tries to study integrable Kepler billiards. And the first non-trivial example is due to Galotti-Josselin from last year, stating that if you're in a plane with a Kepler force field underlying, and if you put a line as a wall of reflection, then the system is actually integrable. Another trivial case which one might add is, of course, if we add a circle centered at the attractive center, then the system will be integrable. So in this last case, we take, for example, angular momentum squared as the additional conserved quantity. But the Galotti-Jordan's first integral in this first case is actually rather complicated and highly non-trivial. So well, now what we could do is that we just bring this Hooke, so this integrable Hooke billiards via the complex square mapping to enrich the list of integrable Kepler billiards. And this I've done with Ari Takeuchi from Karlsruhe, and by doing so, you see again it's very simple, but by doing so we get a lot of more examples of integrable Kepler billiards, which also relates, for example, these two previous known cases of a line and a centered circle. Namely, because the complex square mapping sends these centered conic sections into conic sections focused at the attractive center. Therefore, all these ones with focused conic section reflection walls are integrable for this Kepler billiards. And we have also extended this a bit to the two-center problem. And the result is the following, which is again with Ari Takeuchi. So the result is that non-trivial integral billiards of the two-center problems are, for example, those with confocal conic section reflection walls. So here confocal means that the foci of these conic sections are the centers of the two-center problem. And indeed, one could also make arbitrary combinations of this type of reflection walls. So it doesn't have to be simple, and you can take a combination of these, and the system remains well. So the corresponding billiard system will remain to be integrable. And the reason is that the system is separable in polar coordinates after being transformed by the Birkhoff's mapping. So this is the Hamiltonian of the two-center problem once we fix the energy. And we may then try to pull back by the cotangent lift of this Birkhoff mapping. So that is sent to z plus z minus 1 over 2. And then, then we get a kind of a complicated system. But somehow this system, if we for this system, if we pass consequently to polar coordinates, then the system appears to be separable. With so here, for example, so r theta are the polar coordinates. So r is a radius and theta is a polar angle, and pr and p theta are the corresponding conjugate variables. And what one sees here is that it is a separability, and which then gives us two conserved quantities, both quadratic in the momenta, so in PR and in P theta. And therefore, consequently, the coordinate lines of in the polar coordinates, namely centered circles and also lines through the center, are integrable reflection walls for this system which we have obtained in the end. Simply because so if we reflect against one of these coordinates, then just PR will be sent to minus PR and P theta will be sent to minus P theta, essentially this type of stuff. So so therefore clearly these small so separated Hamiltonians will be preserved, and then the mapping will this Birkhoff mapping will send these center circles and lines through the center precisely to confocal conic sections. Therefore, we get our result, which is again very simple. Okay, and then I would like to talk a bit about another result, which concerns with a forgotten theorem of Darboux and its application. So here's a forgotten theorem of Darboux from 1889, which I'll try to state it in a simplest form. So so before we say we have always say so use the notation that V is a potential, so it's a potential energy, and minus of V is traditionally called the force function, and if we have a Riemannian manifold, so mg, and we have assigned to it a force function u, which is only a function, so u is a function on m, then this will give us a mechanical system. So just by stating that the covariant derivative of the velocity with respect to itself equals to the gradient of u with respect to the Riemannian metric G. And Darboux's theorem tells us that mgu and mu of G 1 over u, so these are very different systems. For example, the underlying manifold are the same, but the metric changes and the force function changes. However, they will have the same orbits, so in M, up to some time parameterization in the configuration space. There are several proofs. So Darboux's original proof make use of the Jacobi mobility metric. So essentially, one sees that these systems will have so essentially the same Jacobi mobility metric. And another proof is to try to mimic the one of this procedure of pulling back, so change time and pulling back systems in the Hamiltonian formalism, which I think in this case there's also even no need to pull back stuff. So essentially just this changing time trick, and then try to further normalize the constant introduced. So there are two ways. Both are very simple, and we get this result, which is highly non-trivial, stating that these two systems have the same unparameterized orbits. And therefore, we call this Darboux inversion. So therefore we call this system, for example, mu of G 1 over u, the Darboux inversion of mgu. So it's called inversion because if we apply it twice, then one gets back to itself. Another thing is that here we have assumed that u is positive. But when when u is negative, essentially one could multiply with minus u, but then this would lead to a discussion about the domains and so on, which complicates things. So maybe we should maybe we don't discuss this too much here. And then this somehow explains this Hooke-Kepler correspondence through a further double-Gauver procedure. So here's a few pictures. So here we start from the Kepler problem with these red circles meant to be, let's say, some orbits from the Kepler problem, and then what we can do is that we can now apply this theorem of Darboux, which will then make the center singular, because there, for example, if we take u as 1 over the norm of q, then we have to multiply the metric also by this quantity, which will then make this attractive center now becomes a singular point already for the metric, and but then it is regular everywhere. Therefore, we get this kind of Riemannian surface, and it is clearly rotational invariant, and one can also compute this curvature. It appears that the curvature is actually 0. So in the end, what we get is a cone. And because it's curvature 0, it can be developed. So if we cut it along one of these lines, then we can actually develop it out. And the angles can also be computed. It appears that once we develop this out, then the angle is precisely is precisely pi. So what we get is that this picture, if we cut it along one of these lines, for example, this line here, then what we get is a system on a half plane, for which we should identify points on this line, which is symmetric, which is back to this red point, so to the center here. And therefore, to make it into a system defined on the whole plane, a simplest way is to take double gather and just connect the orbit to this other side, and in the end we get now a problem in the plane, which is now everywhere regular, and this is the Hooke problem when we start from the Kepler problem. So this is somehow what underlies this procedure of Z to Z2. So we see that Z to Z2 is 2 to 1. Is a 2 to 1 mapping branched at 0, and here somehow explains this procedure through this double gather procedure. And with Alain, what we have looked is rather this problem of Darboux systems. So we assume, for example, Mg is an abstract surface of revolution, so it's rotationally invariant a surface, and on such a surface of revolution, so it can be abstract, meaning that it does not have to admit embedding into R3. And on this, a rotation invariant system, MGU, is called a Darboux system if there is a neighborhood of circular orbits that are filled up with closed orbits. So if a neighborhood of circular orbits are filled up with closed orbits, meaning that in all of these rotational invariant systems, suppose U is suppose the corresponding force is attractive, then there will always be circular orbits, and what we want is that if you perturb the initial values of the circular orbit a little bit, then the orbits somehow close up still. So Darboux in 1877 studied the existence of these Darboux systems and obtained a classification of such systems. And so he posed the question and also answered it essentially. And this generalizes a classical question of Bertrand 4 years ago. And then this subject has been further studied by many other people. And for example, Zhao, Pfister, Funk, but these people are more towards the situation of free motion, so geodesics. And then Perlik, Santoprit, Zagriasti, Kudryavtseva, Fedoseev, and so on and so on. And this really spans from the time of Darboux till nowadays. So the classification result, we can say just very roughly the following. So there can exist at most 2 of non-trivial potentials, so up to constant, on an abstract surface of revolution, which gives rise to such type of Darboux systems, and with some prescribed with some explicitly given conditions. And when there are 2 of them, then the curvature of the surface must be constant, and the corresponding system is one of the Kepler type, so it has 1 singularities at some so at a point at this point at the center of the surface of revolution, and another one will be of the type of the harmonic oscillators, so which is regular here. And moreover, there exist also families of surfaces which admit only one of such potentials, so for these Darboux systems. And in this case, the system will be of the type of harmonic oscillators. So the center will not be singular for such systems. And all these are given by very precise formulas and so on, but I cannot reproduce it here. And then we have these 2 nodes, Darboux 1889 and Darboux 1877. Again, a very simple observation is that Clearly, because this Darboux inversion does not change the geometry of the orbit. Therefore, if we start from a Darboux system and we take its Darboux inversion, then we get again a Darboux system. So then Darboux never applied his inversion to 1889, of 1889 to his study of 1877 about this subject. And this we have carried out with Albouy, and it's now trying to finish writing. And the result is that all Darboux systems can be derived from Kepler problem on constant curvature spaces via Darboux inversions. And there will be just some problem of taking rational governors and so on. And for this, let's just simply state it by saying that up to domain restrictions. So if one restricts the system into some sufficiently small neighborhood, then this will be derived from a corresponding small neighborhood of the Kepler problem on some constant curvature spaces. Here, there's one thing which one has to remark, is that in this previous things, here we have this u, we have this function u. So this is our false function. But if u is a false function, we may take u plus some constant, which is again a false function of the same system. But they will have different Darboux inversions. Therefore, from one system, we actually get a one-parameter family of its Darboux inversions. It is with this procedure we get many of these Darboux systems from Kepler problems on constant curvature spaces. And some of them does not have constant curvatures and so on. Okay, so here's a very short timeline about this mapping. Apparently, the duality of homogeneous potentials was a subject already looked by McLaurin, and then Hooke proposed to understand the Hooke-Kepler correspondence by this mapping, but more generally the correspondence by conformal transformations in the plane. And to this note, Darboux adds 2 pages which states his forgotten theorem that we have said. And then from the start of the 20th century, Levi-Civita used these 2 regularized collisions in the planar restricted three-body problems, which later on becomes very popular. And in 1953, Faure carried this Hooke-Kepler correspondence also to the quantum setting. And in 1964 and 65, Kurzheimer and Stiefel, they generalized these to the spatial Kepler problems. Yeah, okay. So I stop here. Thank you very much.
Very nice talk. Any question?
May I ask you something, Lei? I'm Vivina.
Yes.
When you talked about the Perturque problem, you said that in a recent paper, I think, you proved the existence of infinitely many periodic orbits accumulating at the attracting center.
Yes.
It is. What do you mean as periodic orbit that accumulate to the attracting center? That the orbit is smaller and smaller, or just that have a sequence of I don't know.
Yes. So, let's say in an arbitrary small neighborhood of the attractive center, then you can find infinitely many generalized periodic orbits bounded in this neighborhood.
Ah, okay.
Yeah.
Can you send me this paper if it is already written?
Yes.
Can you send me by mail?
Yes, I can. Yes.
Thank you very much.
It's recently accepted, so I can send you the last version. Yes.
Thank you.
Maybe I can ask a question.
Okay.
Yes, if you take this billiard with 2 fixed center and an ellipse as a boundary, then when the velocity goes to infinity, then you get, what do you get? Of course.
I don't understand you. You take where
You take
does
the
velocity?
billiard with
Yes.
two fixed center inside,
Yes.
and the boundary is an ellipse with two foci.
Yeah. This is not allowed because it has to be confocal, which means that in that case, it has to be a line segment connecting the two foci.
Huh?
So this is not allowed. So it has to be a line segment connecting the two the two centers. So what we have said is that it has to be this has to be confocal with foci at the two centers.
Yes. So I take this ellipse confocal, any ellipse confocal.
Yes.
And then, yes, you have a billiard. You define a billiard with bouncing on the ellipse inside and attracted by the two centers. And then you take velocity going to infinity. Then
I take velocity going to infinity.
Yes. Then you obtain the usual billiard on integrable billiard.
Yeah, sure. I see what you mean. I see what you mean. Yes. So yes. So let's say then we could, for example, move. So for those trajectories which does not enter into some prescribed neighborhood of the centers, then in the limit you will get a free billiard inside the ellipse. For example, this is so coherent with the integrability of a free billiard inside the ellipse. Yes.
Any question? So maybe just a remark in your timeline. Maybe last time Vivina spoke and I commented about Levi-Civita 1920. So it's interesting to mention that Levi-Civita 1920, it's about 3 dimensions, and it uses Darboux forgotten theorem.
Okay.
It is based on Darboux forgotten theorem.
Okay.
It's not a very, I'm not absolutely sure because it's a strange way of mentioning the thing, but in the middle of the paper you see it.
Okay. So only this Italian could remember this theorem at the time.
But it's written in French.
Yeah. Okay.
Any question?
But also really about this timeline, I have to say that with Alain, we're preparing a much more extended timelines about this mapping as well as about these problems of Darboux systems in this manuscript. So this is just a very short part of it.
Any question? So let's thank the speaker again.